Hello everyone. For this tutorial video, I like to talk about how Kirchhoff's laws can be applied to solve complicated circuits, as well as an explanation/justification for why they are expressed the way they are. The first one, called Kirchhoff's voltage law, or KVL for short, states that the algebraic sum of all voltages in a loop or circuit must be zero, which may sound like nonsense at first because we know even for the most simplest circuits there must be voltage for electricity to happen. But if we know, for example, that a resistance is a voltage drop and not a voltage increase, it might make more sense somewhat. For example, if we look at this simple series circuit, we see that we have positive 45 volts at the source, but we have negative voltages across each resistor because it is a voltage drop. So once we add all of these voltages individually like we would normally do for a series circuit, we conclude that the total voltage in the circuit sums up to 0 volts exactly. If we look at a parallel circuit and diagram out all the voltages in it, starting from the negative end and ending at the positive end, as you would normally do when you analyze a circuit, we see at the first resistor, it is exactly negative 6 volts. At the source, it is exactly positive 6 volts. And for all of the wires in between the resistors and not on the resistors themselves, it is exactly 0 volts, as we are making the assumption that all of the connections between the resistors have no resistance. So now, we should logically conclude that the total sum of all the voltages in this circuit is also 0 from this careful analysis. So since we have justified Kirchhoff's voltage law is true for both series and parallel circuits, it should logically follow that it is valid for series parallel circuits as well. Although of course, like with normal series parallel circuit analysis, you have to be careful about applying different rules for parallel and series circuits when appropriate, and not simply assuming the voltages will add up neatly, as if it were a series circuit alone. This brings us next to Kirchhoff's current law, which states that the sum of currents in a node must be 0, where a node means a straight line path like a branch of a parallel circuit, which if we looked at a simple parallel circuit rather than a series parallel circuit, we should verify is true because resistance opposes the flow of current. So the current across a resistor is negative explicitly, in comparison to the positive current from the voltage source. And we can see for series circuits, since the current is the same throughout it, we can state that the current drop exists only along one resistor, and the current drop along all the other resistors is 0. Or more technically, the current drop across the total resistance is negative, after and only after you have combined all the resistors into one total resistance. So, the negative current adds up to the positive current and you get 0. And so, because we've verified that Kirchhoff's current law works for both series and parallel circuits, it should follow that it works for series parallel circuits exactly like the voltage law. Although of course, we have to pay attention to combining complicated series into single nodes when appropriate. And just like with voltage, we cannot assume that currents will always add up neatly. Now that I've explained all of the theoretical methods of evaluating series parallel circuits, I can talk about more complicated electrical engineering concepts rather than simple resistor circuits like we've been talking about so far, such as batteries, how temperature affects resistance, capacitors, and how magnetism relates to electricity, which is formally called inductance. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.